Welcome my dear learners for this course on Tribology. So far we have completed our discussion on hydrodynamic bearings. Now today's lecture, let us start discussing hydrostatic bearings. Now if the pressure developed by the oil film hydrodynamically in the bearing is not enough to withstand the load, what to do in such conditions? In such conditions we should pressurize the oil such a way that the pressure developed by the oil should be enough to withstand the load acting on the journal. If we supply the pressurized oil externally to the journal and bearing, then the bearings which works under external pressure are termed as external pressurized bearings or hydrostatic bearings. So if the oil film pressure developed hydrodynamically is not enough to withstand the load acting on the journal, in such cases we should supply oil externally or pressurize the oil film externally with the use of pump or external accessories. The bearings which works on these principle, that is externally pressurized bearings, are termed as hydrostatic bearings. Let us discuss hydrostatic bearings in today's lecture. So the topic of today's lecture is hydrostatic bearings. Hydrostatic bearings. So hydrostatic bearings are nothing but external pressurized bearings, or they are also called as externally pressurized bearings. Externally pressurized bearings. Hope you clearly understand what is the meaning of hydrostatic bearings. Now the advantage of hydrostatic bearing over hydrodynamic bearing is that, coming for the advantage of hydrostatic bearings, so since we are pressurizing the liquid or oil externally with the help of pump, the contact between the journal and the bearing is very small, or there will not be any contact between the journal and the bearing. So this helps in starting and stopping of the bearing. So therefore this possesses very low frictional characteristics. So this possesses very low frictional characteristics. Very low frictional characteristics. And also it can carry heavy load under low speed, because we are pressurizing the oil with the help of pump, hence it can withstand high loads. It can carry heavy loads at low speeds. Carry heavy loads at low speeds, and it has high positional accuracy. It has high positional accuracy. It has very high positional accuracy. Because of low frictional characteristics, these bearings are employed in gyroscope. Because of their capability of handling very high loads at low speeds, these are employed in telescope. Because of their high positional accuracy, these are employed in machine tools. So coming for the application of hydrostatic bearings, because of very low frictional characteristics, this is used in gyroscope. Because of its capability of handling high loads at low speeds, it is used in telescopes. Because of their high positional accuracy, these are employed in machine tools. So these are the advantages and applications of external pressurized or hydrostatic bearings. Now coming for the disadvantages of these bearings. Disadvantages of these bearings. So these bearings require external accessories, pump, etc., in order to pressurize the liquid or fluid, oil or lubricant. So therefore this requires external accessories. requires external or additional accessories such as pumps, oil pump, and also they are high power consuming bearings. So they consume high power because we want to run pump in order to pressurize the fluid. Therefore, the overall power consumption in operating this hydrostatic bearing is high. So these are the advantages, application and disadvantages of hydrostatic bearing or externally pressurized bearing. Now coming for pressurizing the liquid or oil in order to withstand the load acting on the journal can be done in two different ways. That is system of, next topic is system of hydrostatic lubrication. System of hydrostatic lubrication. Coming for system of hydrostatic lubrication, we have two different types, that is lubrication at constant pressure and we have lubrication at constant oil flow. Or at constant oil flow rate. Lubrication at constant oil flow rate or at constant discharge. Now to understand lubrication at constant pressure and lubrication at constant oil flow rate, let us consider journal, that is runner. Let us have runner or rotor, we can say. This is nothing but shaft or journal, and let us have the stationary element on which we have pocket. Like this we have pocket. On this bearing, let us have a oil hole like this. We have a oil hole and we have a restrictor in order to maintain the pressure constant, and we have supply pressure. So externally using pump will supply oil through the restrictor. Through the restrictor to the pocket. To the pocket. To the pocket. The pressure inside this is denoted by P naught. The supply pressure and the pocket pressure are not same. Supply pressure is not equal to pocket pressure in case of lubrication at constant pressure. In case of lubrication at constant pressure, we have, so this is oil film thickness H, oil film thickness, oil film thickness H, and let us call it as stator or stationary part. So this is journal and this is bearing. So we are supplying the oil, pressurized oil, by using pump through the restrictor. By using restrictor, I can maintain the pressure in the pocket constant. Now when load increases, the oil film thickness will decrease, thereby pressure will decrease. So by using restrictor, I can increase the pressure such a way that the oil film will again increase and maintain the equilibrium position. So using restrictor, I can maintain the constant pressure. The inlet pressure is nothing but pocket pressure P naught. Now in case of lubrication at constant oil flow rate, lubrication at constant oil flow rate does not have restrictor. So we have rotor or journal, it is also called as shaft, and we have on the stator we have pocket like this. let us have pocket like this. Through the oil hole, we will be supplying the oil with the help of let us say we have some pump or external accessory to supply pressure, and we have pocket, and pocket pressure is P0, and this is oil film thickness H. These are called land or fills. Now in case of lubrication at constant oil flow rate, we don't have restrictor. In case of this lubrication at constant oil flow rate, the supply pressure is equal to pocket pressure because there is no restrictor to regulate the flow or maintain the pressure. Now, in order to maintain the constant oil flow rate, we will be using pressure compensating valve. We will be using what? Pressure compensating valve will be employed here. Pressure compensating valves are used in order to maintain the constant oil flow rate. As the load increases on the journal or rotor or shaft, the oil film thickness will decreases, thereby pressure will decrease. Now by using the pressure compensating valve, we can maintain the oil flow rate constant and increase the thickness, oil film thickness, thereby withstand the load acting on the journal. In case of lubrication at constant pressure, we will be using restrictor in order to maintain the constant pressure at the pocket, thereby maintaining the equilibrium between the pocket pressure, oil film thickness and load. So here load, oil film thickness and pocket pressure are all interrelated. So this is the system of hydrostatic lubrication. The bearings working on these principles are termed as hydrostatic bearings. And very important note I should mention at this point is that the rate of change of load acting on the rotor with reference to oil film thickness is termed as bearing stiffness. So bearing stiffness, they can ask you to define bearing stiffness. Bearing stiffness is defined as the rate at which load changes with oil film thickness. The rate at which load changes with oil film thickness is termed as bearing stiffness. Kindly make a note. The better representation is available in our data handbook written by K. Lingaya, volume 2, 8th edition, chapter 24. If you referring page 24.46, figure 24.48 for better representation of hydrostatic bearing. Now let me write this figure and derive expression for discharge and pressure distribution in today's lecture. So with this very brief introduction to hydrostatic lubrication and hydrostatic bearing, let me derive an expression for discharge and also for pressure. That is, now if I recollect the figure from page number 24.46, referring to figure 24.48, we have a shaft like this. On the shaft we have pocket. Pocket can be on both shaft as well as on the rotor, and we have a oil film thickness. We have a oil film thickness like this, and we have a pocket on the stationary part. H, and the journal is rotating with velocity or with speed, angular speed omega, and it is acted upon by load W. So like this, let us consider as shown in figure 24.48 of our data handbook. So this is pocket. Now if I consider this one, we have the projections like this. So this pocket diameter is given by d1. d1 is the pocket diameter, and this shaft diameter is given by d2. Shaft diameter is given by d2. So this diameter is d1 and this diameter is d2. d2 is shaft diameter, d1 is pocket diameter. So now we have arrangement like this. So I noted down the sketch from the data handbook. So this sketch is available in page number 24.46, referring to figure 24.48. Now let us derive an expression for discharge. Expression for discharge. Now in order to derive expression for discharge, I can take overall discharge is equal to, integral is from 0 to h, discharge on the small elemental length. Now if I consider the small elemental ring here, if I consider a small elemental ring between this gap, between the diameter of the pocket and diameter of the journal, if I take a small elemental ring like this, let us have this as radius of pocket r1, this as radius of journal or shaft r2, and let us take an elemental ring, a small elemental ring for analysis. A small elemental ring I will consider for analysis. Like this, at a radius r, from the center, whose thickness can be taken as dx, or let me take it as dy. I will take a small elemental ring of oil film at a radius r. r1 is the pocket radius, r2 is the shaft radius. So oil film, I have taken a small elemental ring to determine the oil flow rate. Now this can be written as what? Discharge is equal to, integral is from 0 to h, dv is from 0 to h, dq can be written as velocity times the elemental area. Velocity times the elemental area. Now elemental area dA is nothing but circumference into thickness, so therefore it is 2 pi r dy. Now what is the formula for velocity? So this is the case of coed flow. For coed flow, where the flow is between two parallel plates, where one plate is fixed, another plate is moving, we know what is the equation for velocity. The equation for velocity is also derived when I have derived an expression for Reynolds equation in 2 dimension. So recollecting the equation for velocity for coed flow, we have 1 by 2 eta dp by dx y square minus hy. This is pressure induced flow plus viscous drag u of h minus y by h. These you people already know. Now to derive these expressions, we have some assumptions. Those assumptions are, the very first assumption is the oil flow is laminar. The second assumption is that pocket is deep enough so that pressure in the pocket is uniform. Pocket is deep enough so that pressure in the pocket is uniform, and it has very low frictional characteristics, very low frictional characteristics, therefore viscous drag is negligible. Therefore viscous drag is neglected. So these are the three basic assumptions which are required to derive expression for discharge, pressure distribution, load carrying capacity and frictional power loss. Now let us derive one by one. First let me take up expression for discharge. Now if you carefully observe, our third assumption is that since we have very low frictional characteristics, the viscous drag is neglected, so therefore neglect the viscous drag. So this is viscous drag. Viscous drag is neglected from our assumption because of very low frictional characteristics. Viscous drag is neglected, whereas this part account for pressure induced flow. Hope it is clear. So now substitute these two, and if I integrate, I will get expression for discharge Q as integrals from 0 to h. Value of U is 1 by 2 eta dp by dx y square minus hy 2 pi r dy. 2 pi r dy. Now if I take constant outside and integrate, 1 by 2 eta dp by dx into 2 pi r, if I take out and integrate y square minus hy, I will end up with y cube by 3 minus h into y square by 2, 0 to h. Now further simplification will yield us Q is equal to 1 by 2 eta dp by dx 2 pi r times h cube by 3 minus h cube by 2. H cube by 3 minus h cube by 2. So therefore Q will be equal to, so I will get the equation as 2 pi r by 2 eta dp by dx of 2h cube minus 3h cube by 6. So therefore Q will be equal to minus pi r h cube by 6 eta dp by dx. Take it as equation number 1. Now if I rearrange the term for pressure, we will get dp is equal to minus 6 eta q divided by pi r h cube dx. Pi r h cube dx. Since the coordinate system is cylindrical in nature, let me replace dx by dr for pressure distribution. Since coordinate system is cylindrical, use dr instead of dx. So if I do that, I'll get the equation as so we are deriving equation for discharge and pressure. We are deriving equation for discharge and pressure. So therefore, what I can write? I can write it as dP is equal to minus 6 eta q divided by pi r h cube dr. Now if I integrate on both sides, I will get dP is equal to minus 6 eta q by pi h cube integral of dr by r. So therefore pressure P is equal to minus 6 eta q by pi h cube ln r plus constant of integration. Now I have to find constant of integration, for which I will use boundary condition. To find C, use boundary condition. Use boundary condition. That is, if I use the boundary condition, we have first boundary condition at radius r is equal to r1. At radius r is equal to r1, we have pocket pressure. We have pressure P is equal to P naught, pocket pressure. At r is equal to r2, at outer surface we don't have any pressure. So therefore, second one, at r is equal to r2, P is equal to 0. Let me use the second one, thereby I can get the value of C easily. So therefore, using the second boundary condition, operating here, I will get 0 is equal to minus 6 eta q divided by pi h cube ln of r2 plus C. Hence I will get the constant of integration C as 6 eta q by pi h cube ln of r2. So hence if I resubstitute to pressure, I will get the pressure equation as P is equal to 6 eta q divided by pi h cube ln r2 minus ln r1. Ln r2 minus ln r. Now let us take this as equation number 2. And substitute the value of second boundary condition. Use first boundary condition, because using the second boundary condition I have found out the value of C. Now use the first boundary condition. So using first boundary condition, first boundary condition, I will get P is equal to pocket pressure P naught at R is equal to R1. I will get 6 eta q by pi h cube ln of R2 minus ln of R1. So hence I will get the equation for discharge. So therefore, what is the equation for discharge you are going to get? So therefore, discharge expression will become discharge equation Q will be what? Rearrange it. Q is equal to pi P naught HQ divided by 6 eta ln of R2 by R1, or it is also be written as ln of D2 by D1. This is nothing but equation 24.140 of our data handbook. So therefore we have derived expression for discharge, and this is the expression for pressure at any given radius once discharge is known. Now resubstitute this to equation 2. Resubstituting to equation 2, resubstituting in equation 2, if I resubstitute the discharge equation, I will get the pressure equation P as 6 eta by pi h cube, 6 eta by pi h cube times Q is this one, right? Pi P naught h cube by 6 eta ln of R2 by R1 into ln of R2 by R. So if I simplify, pi h cube will get cancelled, 6 eta and 6 eta will get cancelled. So therefore I end up with the relation between the pressure P and the pocket pressure P naught as P is equal to ln of R2 by R divided by ln of R2 by R1 into P naught. So this is the relationship between pressure P and inlet pressure P naught or pocket pressure P naught, and this is the expression for discharge. This equation is very important to solve numerical problems on oil flow rate. So let me stop this lecture here. In our next lecture, I will take up expression for load carrying capacity and frictional force. That's all from this lecture. Thank you all.